In this video, I'm going to solve this problem, integral 0 to a log of 1 plus ax by 1 plus x squared dx equal to half of log of 1 plus a squared tan inverse of a, and then on replacing x a by 1, then you get integral 0 to 1 log of 1 plus x by 1 plus x squared dx is equal to 5 by 8 log 2. So before here a will be a parameter. So note down here that a will act as a parameter. Now let us just recall this Leibniz theorem. It states like this: if phi of y is called integral gy to hy fxy dx, where the partial derivatives of gy hy with respect to y exist and are also continuous, that means the partial derivatives of gy and hy, the lower and upper limit of this integral, exist and are continuous, then in that case the derivative of this one, phi prime of y, will be given by the formula gy to hy f suffix y xy dx. F suffix y here means the partial derivative of f with respect to y plus into the derivative of this upper limit h prime of y into f of hyy minus g prime of y, that is the derivative of the lower limit, into f of gyy. So let us apply this one, but you please note down that here in place of g of y it is 0 and in place of h of y it is a, where the parameter in this case is not y, and as if you compare with the Leibniz theorem, but it will be a. Okay. So now let us solve this problem using the Leibniz theorem. So first step, what we need to do is you take, let fax equal to log of 1 plus ax divided by 1 plus x squared. Then if you differentiate this one, f suffix a of ax, this will be equal to what? Differentiate this with respect to the a, then you get 1 by 1 plus ax, because differentiation of log of 1 plus ax will be 1 by 1 plus ax into that 1 plus x squared. X will act as a constant in this case, into the derivative of this 1 with respect to a, it will be x. So this implies that f suffix a, that is the partial derivative of f with respect to a, is equal to x by 1 plus ax into 1 plus x squared. Now let us express this one now. So now next step, this is step 1. Step 2 will be what you need to do. We write now phi of a is that given integral 0 to a f of ax dx, which is called integral 0 to a log of 1 plus ax divided by 1 plus x squared dx. So name this, let us name this as equation 1. Then what is phi prime of a? Phi prime of a, if you apply this Leibniz theorem, you replace this one here, it will be 0. So the first one will be instead of fy, it will be f suffix a. So you have to write it by that one, and g of y here, it will be 0, and h of y, it is that a. So this will be equal to integral 0 to a, the first term will be f suffix a of ax dx plus what is h prime of y? H prime of y, that means the derivative of, in this case, h prime of a is equal to a. So if you differentiate this a with respect to a, you will get 1. So you will get here 1 into f of a, f of ax, plus what will be there? What will be g prime of y here? G prime of y is equal to 0, since the lower limit is equal to 0. So in that case, the third term will be 0. Please correct here, because hy of y, but here y is equal to a. This one should be a. Fa, a, you replace x also by a. So finally, by Leibniz theorem, we have the expression of phi prime of a is equal to this one. Or I can further simplify, it will be phi prime of a is equal to integral 0 to a what is what is f suffix a of ax? From this one, it is equal to this integral. So it will be equal to x divided by 1 plus ax into 1 plus x squared dx plus 1 times of FAA. What is f of a? F of a is this one, FAX. So, but you need to replace a by what? By x. So, it will become 1 plus a square by 1 plus a square. So, in that case, it will become 1 into log of 1 plus a into a divided by 1 plus a square. Let me further simplify it. It will be integral 0 to a, then x dx divided by 1 plus ax into 1 plus x square plus log of 1 plus a square divided by 1 plus a square. So this implies that 5 prime excuse me, 5 prime of a is equal to this. Let me name this as equation 2. Now next, what we need to do, we need since this one is already outside the integral sign, so we don't need to evaluate it anymore. But let me now evaluate first this one. Now, note that the term inside the integral x by 1 plus ax, by using the method of partial fraction, this is equal to minus a divided by 1 plus a squared into 1 plus ax, then plus x plus a divided by 1 plus a square into 1 plus x square. Okay. Just see this one. This term x by 1 plus ax into 1 plus x square can be expressed as minus a upon c. It is 1 plus a square into 1 plus ax, this one. Plus x plus a divided by 1 plus a square into 1 plus x square. If you here, what will be the LCM? The LCM in this case is 1 plus ax into 1 plus x square. So multiply this one by 1 plus x square and this term by 1 plus ax. Then you simplify it, then you get exactly x upon 1 plus ax into 1 plus x square. So by method of partial fraction, we got this one. Now, see, the expression of this can be written now as a sum of these two functions, minus a upon this one plus x plus a upon this term. So let us integrate it now, because we need to find the integral of that one. Therefore, integral of 0 to a x dx divided by 1 plus ax into 1 plus x square, this is equal to minus a, since we have to integrate with respect to x, so it will be 1 plus a square. You can take it outside the integral sign. 0 to a dx by 1 plus ax plus the next one will be 1 by 1 plus a square. That one I can take it outside the integral sign. Then x plus a divided by 1 plus x square dx. Let me simplify this one. It will be minus a by 1 plus a square, then integral 0 to a dx divided by 1 plus ax. This will remain as it is. Now the next one will be 1 by 1 plus a square. Now here we have x dx. So I can write that one as integral 0 to a, here also integral 0 to a, x dx divided by 1 plus x square plus 1 by 1 plus a square, integral 0 to a, it will be a dx divided by 1 plus x square. I split this one into two parts. One is x upon this term plus dx plus a dx by 1 plus a square into 1 plus x square. So let us find out what will be the integral of these three terms here. It will be minus a by 1 plus a square, integral 0 to a, then this one can be written as a d of 1 plus ax. If you differentiate this with respect to x, you get a dx. So in that case, you have to divide it by a. Then by 1 plus ax plus 1 by 1 plus a square into, in this case it will be half will be common factor. Why? Because you'll have it as d of 1 plus x squared. So d of 1 plus x squared will give you 2x dx. X dx will be there, but 2 and 2 can be cancelled. So it will be 1 plus x squared. And the last one is 1 plus 1 by 1 plus a squared. Now a also can be taken outside. Then integral of 0 to a dx by 1 plus x squared. Let us simplify it. So this is equal to minus a by a and a can be cancelled. This a will not be there, so it will be just minus 1 by 1 plus a square integral 0 to a okay. Now this one is sort of form d integral du by u, so it will be log of u. So the first one will give you log of 1 plus ax from 0 to a plus, now this will be 1 by 2 times of 1 plus a square. Then what is the integral of this one? Again it is sort of form du by u. This is a. So this will be log of 1 plus x square from 0 to a plus the last one, it is a by 1 plus a square. Now what is the integral of dx by 1 plus x square? It is tan inverse of x. So here you'll get it as tan inverse of x here from 0 to a. Let us substitute the limit of integration. So this is equal to minus 1 by 1 plus a square, and on simplifying this one, substitute the limit of integration here by a, then the upper limit will be 1 plus a square, and if you substitute x is equal to 0, then you'll get log of 1 plus 0. So log of 1 again will be 0. So from here you'll see that you'll get only this term log of 1 plus a square, then plus 1 by 2 times of 1 plus a square. Now again here if you substitute the upper limit then for x, then it will be 1 plus a square. And if you substitute x by 0, the lower limit, then it will be log of 1 again 0. So you get only one term here. That will be log of 1 plus a square. Then plus a by 1 plus a square into tan inverse of a. And if I replace x by 0, the lower limit, then tan inverse of 0 will be 0. So see that after simplifying this one, we got all this 3. So this implies that integral x dx divided by 1 plus ax into 1 plus x square from 0 to a is equal to this whole thing. Now next we differentiate this one. Now you substitute in this equation 2, we have phi prime of a is equal to integral of this. We have evaluated the value of this one. So now let us substitute the value of this integral in equation 2. So you can write now putting the above values of the above value of integral 0 to a x dx by 1 plus ax into 1 plus x square in equation 2. We have phi prime of a is equal to minus log of 1 plus a square divided by 1 plus a square plus 1 by 2 into 1 plus a square into log of 1 plus a square plus a by 1 plus a square into tan inverse of a, that is the integral of that first term. And then what is the second term there? The second term in equation 2 is log of 1 plus a square by 1 plus a square. So you add up this one. So it will be plus, it is log of 1 plus a square divided by 1 plus a square. Now see, the first term and this last term can be cancelled. So what we have now is phi prime of a is equal to log of 1 plus a square divided by 2 times of 1 plus a square, then plus a by a tan inverse of a by 1 plus a square. Now see, this one gives you the value of phi prime of a. Just to get back phi of a from here, you need to integrate both sides with respect to a. So now I'm going to write here, in order to get phi of a from the above expression, we integrate it with respect to a. So on integrating this one with respect to a, so integral of phi prime of a will be phi of a. So the left hand side will give you phi of a, and on the right hand side it will be integral of log of 1 plus a square dA. Please note down this thing, since it is with respect to a, 1 plus a square plus integral a tan inverse of a upon 1 plus a square plus some constant, say c, where this constant c is to be evaluated using the initial condition. So now let us integrate this one. So this one can be integrated by part. So you take this one, log of 1 plus a square as a first function and half of 1 plus a square as this dA as the second function. So on integrating by part this one, it will give you log of 1 plus a square, half will be there, then integral of dA by 1 plus a square minus this one, integral of, it will be dDA of log of 1 plus a square into the integral of the second function, that is dA by 1 plus a square, half I can take it outside, then the whole thing dA plus, let me keep this one as it is for the time being, a tan inverse, that second integral as integral a tan inverse of a by 1 plus a square plus c. So this is equal to log of 1 plus a square into half. Now this is the form dx by 1 plus x square, which will give you tan inverse of a here. So it will be tan inverse of a minus half into the integral of this one, log of 1 plus a square. It will be 1 by, if you differentiate that one, you get 1 by 1 plus a square into differentiation of 1 plus a square will be twice a. So you get here twice a, then into integral of this term, integral of this one inside the integral sign again will be tan inverse of a. So it will be tan inverse of a dA plus integral a tan inverse of a dA by 1 plus a square plus that c. So now 2 and 2 can be cancelled here. Please note down this should be dA. So this is equal to log of 1 plus a square, then write it as half of this one into tan inverse of a minus integral here, since 2 has been cancelled and the remaining term inside the integral sign will be a tan inverse of a dA in the numerator. So it will be a tan inverse of a dA divided by 1 plus a square dA plus this third integral a tan inverse of a dA divided by 1 plus a square plus c. Now see, the second integral and the third integral can be cancelled. So it gives you phi of a is equal to half log of 1 plus a square into tan inverse of a plus c. Now let me name this as equation, I think equation 3, since we have 1, 2. So this will be equation 3. Now we need to evaluate this constant c. So to evaluate c, we put a is equal to 0. The initial value of a in the lower limit is equal to what? It is 0. You can see from the given integral, that is this one, it is 0. So therefore we put the initial value of a, that is 0, and then see what we'll have now. In equation 3 we have phi of 0 on the left hand side is equal to half log of 1 plus 0 square tan inverse of 0 plus c, or phi of 0 is equal to half into, now log of 1 plus 0, 1 plus 0 square will be 1 and log of 1 will be 0, tan inverse of 0 will be 0, so in this case it will be 0 plus c. It implies that c is equal to phi of 0. But what is the value of phi of 0? Phi of 0, if you see the original equation, not this one, from equation 1, we have phi of a is equal to integral 0 to a log of 1 plus ax by 1 plus x squared dx. If you replace the upper limit, that is a by 0, then 0 integral of 0 to 0, that one will be 0. So you can write from 1 now. We have phi of 0 is equal to 0. But from equation 1, phi of 0 is equal to 0. So this implies that the value of c is equal to 0. Now putting the value of c is equal to 0 in this equation 3, that is this one. So putting the value of c equal to 0 in 3, we have phi of 0 or phi of a is equal to half log of 1 plus a square tan inverse of a plus 0. Okay, so this means that integral 0 to a log of 1 plus ax, from equation 1 we have what is phi of a, is log of 1 plus ax by 1 plus x square dx. This is equal to half log of 1 plus a square into tan inverse of a. So the first part is done now. We have shown that integral 0 to a log of 1 plus ax by 1 plus x square dx is equal to half log of 1 plus a square tan inverse of a. Now to get the second part, we just have to replace a by 1. Now putting 1, let me name this one as star. Putting a is equal to 1 in star, we have integral 0 to 1 log of 1 plus 1 into x, it will be log of 1 plus x by 1 plus x square dx. This is equal to half of log of 1 plus 1 square into tan inverse of 1. So this is equal to half log 2. Tan inverse of 1 is equal to what? It is pi by 4. Since tan inverse of 1 is equal to pi by 4, as tan of pi by 4, that is 45 degrees, is equal to 1. So on taking that tan to the left hand side, then we get the inverse tan inverse of 1 as pi by 4. So this is equal to pi by 4 into half will become pi by 8 into log 2. Hope it is clear now regarding this problem. Here you please note down, in this case in the beginning, for this one. Okay, so I can just write here, note that f(a)x is continuous for 1 plus ax greater than 0. Because what is f of ax? It is log of 1 plus ax by 1 plus x squared. So if this term is greater than 0, then log of this one will be continuous. And similarly, f(a)ax also will be continuous for 1 plus ax greater than 0. Also, f(a)ax, that means the partial derivative also exists and is continuous for all x and a where 1 plus ax is greater than 0. That means it holds for all x and a where the sum 1 plus ax should be greater than 0. So that's why we are able to consider this Leibniz theorem in this problem. And the function is not continuous at some point, then in that case, in some interval, then in that case we cannot apply the Leibniz theorem. But in this case, for all 1 plus ax greater than 0 and for all x and a where the sum is greater than 0, then we can apply this Leibniz theorem. So I hope it will be clear regarding this particular problem, which is the direct application of that Leibniz theorem of integrating the given function using this one